We are very pleased to have Doron Puder talking about detecting primitivity in free group algebras.
Okay, thank you for the invitation, and it's good to see some friends, old friends in the Zoom over there. Okay, so this is a joint work with two of my students, Matan Zaider and Daniel Ernst-West, and Matan was really a prominent figure in this direction, so I highlighted him. And my rough plan for the talk is to start with first definition. So I'm not sure how people here are used to think about free group algebras, and also explain how I got to think about them. I'll hint to why, and then I'll talk about the analog of the Nielsen-Schreier theorem for free group algebras, and then I'll talk about algorithms. And in particular, I will mention the algorithm to detect primitivity. Okay, so let's start with the definition and motivation. Okay, so throughout the talk, F is going to be some free group, fixed. And for most of the examples, I'm going to just think about F2, which is the free group on two generators, which I will denote by X and Y. And K is going to be an arbitrary field. Okay, and so what is the free group algebra? This is the free group algebra. I'm going to denote it by KF, and this is just finite combinations of elements from the free group with coefficients from the field. So I will denote it by sigma of alpha U, where I go over all the elements of the group, and alpha U is the K, and almost all alpha U's are 0. Okay, and so this is the free group algebra. It's helpful to think about it as linear combinations of the vertices of the tree. So you can think about it also as K linear combinations. Of the vertices of the K graph. Okay. And another, so this is the free group algebra. We're going to talk about one-sided ideals. So right ideals or left. So let me remind, so I'm going to denote it by I in Fk, so in Kf. So of course this is an additive group. An additive group, and such that I times Kf is I. And let me give you a few examples. So of course we can take any element. So this is one particular element in my free group algebra, and then I take all the multiplications. I can multiply from the right by the algebra. This is one idea. All the multiplications. Another one is the augmentation ideal, which is just the sum of the elements such that the sum is 0. And as a final example, and this following example shows you that actually you can think about the free group as in a sense, embedded in the free group algebra. In perhaps, I mean, the subgroups of the free group also live in the free group algebras. So for every subgroup of the free group, there is an associated ideal, right ideal, which I will denote by JH, which is generated by okay. So I'm going to use these brackets to say that my ideal is generated by the set. So the right ideal generated by the set. These are all the elements of the form H minus 1. Okay, it turns out that this is very useful. You can take any subgroup and associate it with this ideal. So when you think about this, is actually the ideal. What is this ideal? This is the ideal where you look at for every right coset of H, the total coefficient, the sum of coefficient is 0. So for example, if H is the entire group, you get here what is generated by, you actually get, if H is the entire group, you actually get the augmentation ideal, which I should have denoted by IF. Okay. Any questions so far? Okay, so why do we care about free groups? The free group algebra. So, you know, probably most people don't need any explanation for that, but let me say briefly a few points. Why should we care about free group algebras? So one thing very general is that, of course, this introduces, we can now use tools from linear algebra to study the group. And linear algebra is very useful usually. So in general, I mean, when you think about implementations of the free group or homology and so on, so we often want to move to the free group algebras. And in fact, there is also some, perhaps a particular example, there are some problems with free groups that were solved using free group algebras. And I'll give one example. So this is quite a recent result by Chaikin. He proved a conjecture about, I will say, the compressed inert conjecture in free groups using the free group algebras to actually, okay, I'll not get into what this is exactly. And now, how did we begin to, how did we got interested in free group algebras? So we actually had our own motivation. It started with a project about word measures on GLMQ. So we studied a very simple problem. We take a word in the free group and we put inside, let's say my word is an F2. I put inside two uniformly random elements. These are like random elements, uniformly random from GLMQ. And we start looking at the random element that we get. And we realized that, I mean, it took us a while to realize that what we actually see is properties of, we actually see, get to study the free group algebras. Somehow we can express all kind of, it's very natural once you think about it enough to express all kind of quantities that you get from studying this as sum over ideals in the free group algebras. So this work actually came from this project. We actually needed within this project, we needed to compute some examples, and we didn't know how to do it. For example, we wanted to detect primitivity. We didn't know how to do it, and this is where it came from. Yeah.
Does Q here represent a finite field, or is it saying?
Yeah, it's a finite field, or it's a prime power. Yeah. You need to be, in this case, you need to be finite, so you can take random elements in a natural way, but.
But you're not taking a random product replacement, you're taking random word in A and B.
Here, no, I'm fixing my word, I take A and B random. I fix my word, and for every fixed word, perhaps I'll say at the very end, if I have some time, how this is related to, but.
Replacement. And just if you want to generate random elements, there's this work of Puck and Lubotsky, which uses this property T now for the.
Yeah, so it's not.
Which now explains everything why that actually produces random elements, probably. It explains why that's what everybody uses to generate. What did you want to generate random elements?
No.
Okay.
No. Yeah, no, one of the motivations was to study random walks on these groups, but.
Like, right, so like a question would be like, for example, what is the odds this is the identity? Or something like that.
Yeah, for example.
What is the word?
What is the probability that you get the identity? Oh, yeah, I mean, basically, yeah. Or you look at some moments of this measure and you want to compute them. Okay, and perhaps lastly, I mean, okay, the final point I will not write down is that actually, once you look at it, you see that this is actually a very nice, beautiful creature, the algebras. Okay, so this was some motivation, and now let me go to what I thought. So when I first, I arrived to thinking about free group algebras from here, I didn't know much about it. So I assume, I don't know, I assume at least some of you don't know that there is actually an analog of Nielsen-Schreier. So let me remind first of all what is Nielsen-Schreier. And this is a theorem from the 1920s, which says that if F is free and H is a subgroup, then H is free. So this is a very, very basic theorem about free groups. And of course, I mean, when you think about it the right way, it's a very easy theorem. Somehow people didn't think about it the right way in the 1920s. But okay, but it turned out that there's a counterpart, an analog, and this is by Paul Cohn in 1964 and Jacques Lewin. Okay, I mean, so if they didn't write it together, this is like this. So the thing is that, I mean, I think Cohn published it, but it's not clear whether there are claims that his proof is not correct. And Lewin published a simpler, proof, which is for sure correct, that every one-sided or right ideal of the free group algebra is free. So what does it mean here to be free? So every ideal every right ideal is a right model of KF, but it's a free right model. With a well-defined graph. Okay, so what are the paths? So let's see some examples. So perhaps I was saying before, what does it mean, namely? So there is some set of elements in I, which is the basis, and for every element in I, there is a unique set of coefficients such that and almost all of them must be zero, such that A is the sum over S of and it should be from the Y, so S times B of S. Okay, perhaps I'll give some examples.
Yes. Is the rank always finite?
No,
No.
no. So exactly as in, I mean, as in Nielsen-Schreier, I mean, actually, you can use this to produce examples. So whenever you know, I mean, the rank here, for every finite, for every subgroup of F, you can generate an ideal. And in fact, if you take any basis of H, then this, if you go over the basis, take the basis element minus 1, this will give you a basis for the ideal. So it could be the same way that in free groups you get infinite rank subgroups, will be the same way. So for examples. So let's take the, okay, I already told you about the third example, how do you get a basis. Let's talk about the first two. So what is the basis for the first one? So what is the basis for this one? Okay, just this one. Okay, this is the basis. So we can take S. Okay, this is the basis. Of course, you can express every element as a product of this element by something from the left, because this is how it's defined. And the only thing I need to convince you that this is a unique one, and this is equivalent to saying that if you take any element, take anything here, like let's take B, and B is in the full algebra, then this is zero if and only if B is zero. And this is actually.
That's a Cadison, I mean, isn't that conjectured to be true for all?
I mean, there's Kaplansky.
Kaplansky.
Yeah, this is exactly the Kaplansky zero conjecture.
Which is conjectured as long as you're torsion free. I don't believe it.
Yeah, and it's not the one that was refuted, right?
No, it's not.
Yeah, so this is conjecture for general group algebras. But for free groups, it's quite easy. But
No, it's not for hyperbolic. But
yeah.
So when you say well-defined range, right, you're just saying that all the bases have the same, you're saying that all the bases have the same size, nothing about there being a canonical basis or canonical.
Right, yeah. Just, same cardinality. Every two bases have the same cardinality. Right, okay, so let me just say that this is zero if and only if B is zero, okay? So this is not hard, it's not trivial, but it's not hard for free groups. And for the augmentation ideal, so now I'm talking about the second example here.
Well, some very short paper that was submitted to the annals. I think we took it. That was some counterexample.
Yeah, there was a counterexample by
3 pages.
by Gilles Gard. Yeah, no, but no, he refuted this conjecture, the classic conjecture.
Okay.
Yeah, I'm not sure if it was the zeros conjecture though. So
Yeah, it was something along those lines.
Okay, so IF, so now this is the augmentation ideal. What is the basis here? So actually I told you more generally. So this is, you can take as a basis 1 minus X and 1 minus Y. Okay, so I'll give you an example how to write an element. So every element in here can be written uniquely like that. So here's an example. If I take 1 minus the commutator of a word, so this is 1 minus X times Y X inverse Y inverse minus X inverse Y inverse plus 1 minus Y times X inverse Y inverse minus Y inverse. Okay, you can check it. Actually, in this case, these are the Fox derivatives of the word. Anyway, you can just check that this is true. And before I move on to algorithms, I do want to give you some sense of some idea of the proof, how this is proved. So I didn't know about this theorem. I didn't know what any of this theory about field algebra before I started working with them.
There is some comment on one, but I also didn't follow your discussion. This counterexample, I guess, this comment source is about this unit conjecture, right? This Gardner's examples is a virtually abelian group, right? So zero divisors conjecture is, I believe, very much open for abelian, well, virtually abelian torsion. Abelian, so certainly zero divisors. Okay, so sorry, somebody commented on mine.
Okay, so here is a sketch of the proof. So I'm just why you get that every right idea is free. Not about. I'm not going to talk about the unique rank, the well-defined rank. Sketch of proof of this theorem. So I mean, so let's say we're given a right ideal. Then there is a tree inside the K graph. So a subtree, which is transversal for the quotient model. Okay, so what does it mean? It means that, namely, every coset has a unique representative, which is supported on T. Okay, so why do we have such a tree? Okay, so I'm looking at the K graph. I can look at. I mean, this is a first of all, right? This is by theorem. Okay, of course, if you take just any vertex in the tree, then okay, let's say this is not everything. Proper ideal, then if you just take one vertex, it will be a partial transversal. You can look at all partial transversals, and it's quite easy to show that the condition for Thorne's lemma are satisfied, and you can get a maximum of 1. And then you should prove it's a complete transversal. And then, okay, now after you have this, then you have some, so imagine you have a tree. This is your tree. It's a subtree of the K graph. So they're all, and now it could be, I mean, in some parts it could be infinite, right? It could be, it doesn't have to be a finite tree. But in some parts, there are some bridges. So bridges are edges between the tree and the complement of the tree. So let's say we have here 3 bridges. I mean, it turns out that it turns out, and and one can prove it, that the number of bridges that read X are the same as the number of bridges that read X inverse, and the same for Y. And it turns out that you can take, let's take the coset, let's take this vertex, this is V. So this is the coset of my ideal, and because it's a transversal, I know that there is some linear combination of elements in the tree. Let's say linear combination, let's say 2 times this plus 3 times this minus this, which is equal to this element. And it turns out that if I take V1 minus this linear combination and V2 minus the linear combination that corresponds to V2 and V3 minus the linear combination that corresponds to V3, right? I mean, these are 2 elements from the same coset, so the difference is in I. it turns out that this is the basis. Okay, I mean, of course, I didn't prove it's a basis, but this is I gave you all the thing you need. Now you just need to think a bit to see that you can make a proof of this. Okay, any questions so far? Okay, so okay, so now we know that the free algebra is very similar in many sense. It's similar to the free group. It has this nice property that all the substructures are free as well, in some sense. And then you can start asking, what about algorithms? Okay, so there are some, for free groups, there are infinitely many algorithms to do all kinds of stuff. So perhaps I'll do here a table. So let me mention some algorithms that like some basic algorithms that we have for free groups. So first of all, given as subgroup of the free group, a subset of the free group, let's say finite. Let's say I want to compute the subgroup generated by S. So what is it going to compute? I want to, let's say, get the rank and the basis for the subgroup generated by it. And the analog here would be, again, given subset of the group algebra, compute the ideal which is generated by this subset. So, well, here, how do we do this? Okay, we do it by startings, right? This is the most natural way. You take the bouquet with, you write your words on the bouquet and then you fold and you end up with a finite graph, which easily you can read from it, you can get from it a basis and a rank. So this is a startings. Graphs. Now it turns out on the other side, for free group algebras, there is an algorithm. It's due to Amnon Rosenman. Yeah, 1994. So basically, what he does is, I mean, actually, I mean, if you can get such a basis of this form that comes from some tree and the boundary of a tree, it's actually not very hard to solve this problem. I mean, okay. Sorry, I should have said it in the next slide, in the next point. What Rosenman does is to give you some kind of basis that looks like that. Okay, the second one is, let's say, given age, a subgroup, and a word is this word contained in a subgroup? And here you can do the same. Like once you have the stolen graph, it also solves this problem. And here also you get the same. So again, given I, the elements is a I. And again, I mean, this algorithm of Rosenman. So this is what I meant to say. This is what I accidentally say a minute ago. If you have such a tree, if you have such a basis for your ideal, you get any element is just some points on the K graph. You can actually use these trees to, once every point is out here, you can shorten it by using this relation. You replace V2 times the, if you have some if this is your point on the K graph, V2 times the word that's written here, you can replace it by these points times the same word, and this will give you something that is closer to the tree. And then you can repeat it and get eventually something. Then you have to get zero. If you have to get zero eventually if the element is in the ideal. Okay, I shall skip. There's also a question about intersection. If you get two groups, how do you intersect them? And here, of course, you have to show about ideals.
We'll go to 45 past because we started you 5 minutes late.
Yeah, okay, thanks. Okay, so these are all
Why 5 minutes late? Didn't we start at 2:04 something?
I think that
The first talk was at 15, right?
yeah, it's okay.
it's okay, keep talking.
Okay.
Doron has the 10 minutes more, at least, no?
That's what was just said, Anna. That was literally what was just said.
No, she doesn't have more than 5 minutes.
Oh, yeah.
When
I see the confusion. Yeah. He has more than 5 minutes now. He'll get 5 extra at the end.
So, okay, let me just say very briefly. I mean, this is also easy with curve graphs. This is even easier, because anyway, I don't want to. Yeah, let me go to the more interesting part. Now we have also the question whether we have W in H. We already have a word in H, and the question is W primitive in H? Okay, whether this W is part of a basis of the subgroup. And this is very classically solved by Whitehead. In 1936. So I mean, it's always for the ambient group, but it doesn't really matter. And there are also, so he has this famous cut vertex lemma, and there are also other algorithms, which are probably not as good in terms of efficiency, but there are a few algorithms. And here you can ask the same question. So we are given an ideal and an element in this ideal. And the question is a primitive in this ideal. Okay, so what does it mean to be primitive? It means to be part of a basis. And okay, and this is where this is the result I wanted to talk about. Okay, so can solve this problem. And now I'll talk about what we do. Any questions so far?
You're saying Whitehead did it for groups and you're doing it for the group algebra.
Sorry?
So Whitehead solved the problem for groups and you're solving it for the group algebra.
Yeah, which as far as I know was not, we couldn't find any algorithm. In fact, there are very few, so I should stress, there are very few algorithms for group algebras. I don't think I've seen anything other than Rosenmann's algorithm. So I think this is the only algorithm that I know of, at least for all these simple things, all these basic things, basic questions. So the idea is, use duality between left and right ideals. So here how it goes. This is how it goes. So here I'll give you the algorithm and then I'll say what are the results that are behind it. So we are given some ideal and an element in this ideal. And okay, now we use Rosenmann So Rosenman gives us a basis. We get a basis. Let's call it F1. And moreover, okay, I didn't say it, but Rosenman can also give us and also and the combination of A. So he also gives us the G's such that A is the sum of Fi Gi. Okay, we can also get this easily from the algorithm. And now what we do, we let the dual of I with respect to A, this is the left ideal generated by the coefficients. Okay, so use the coefficient. I mean, the original basis was F. G's are the coefficients that give us A. And this is the dual of A with respect to A. This is a left ideal, which is generated by G1 to GT. And you can notice that, first of all, and I claim, first of all, you notice that A, that this dual also contains A. Why does it contain A?
Just realizing that A is there.
Yeah, right. It's the same expression. The same expression shows you that A is also contained in the ideal, the left ideal generated by the GIs. And now we do the same. Now we reverse the direction. Now we do the same with this ideal, and we take the double dual. Okay, this also contains A as a left ideal. So when we do that again, we get a right ideal that contains A. So this is the right ideal. Defined similarly. And then we show this is a theorem, we'll give theorem 1, that A is primitive if and only if this double dual is A. Is what is generated by only A. Okay, and because of course we can check that. We can take the duals because everything is that you can do it by Rosenman, and then by Rosenman again you get the basis for this element, and it's very easy to see if two ideals are equivalent or the same or not. And I should say more generally, okay, so more generally, we have the following theorems. So first of all, in general, whenever A is an element of the ideal, this is also true for an ideal inside an ideal. There is a unique L, which is the sub-ideal of I, contains A, such that and this is a L is the free factor. Or free summons, if you want. And A does not, or is not contained in any proper free factor of A, of L. And Now, given this, I mean, if A is primitive, this L is just the ideal generated by A, right? This is if A is primitive, and the general theorem is that this I, first of all, it is well defined. I mean, this is not obvious from the way I defined it, because the way I defined it, I chose some basis for I, and I took the coefficients. Perhaps if you take a different basis, I could get another dual, but it's just always the same. And and the rank of this dual. So the side of the basis is always the side of L. And if you take the double dual, you always recover L. Okay, so this is the more general.
How's your thing related to Whitehead?
So it's not, I don't see yet how it's related. It's not related. We also try to think about an algorithm that directly generalizes Whitehead. We think that perhaps you can do this more geometrically, and then.
I mean, yours looks so nice. It's got.
Actually, okay. I mean, it's better. I mean, first of all, you can apply it because, again, every subgroup you can embed it as you can think about it as an idea. You can also use this algorithm for subgroups, but it will not be better than Whitehead in terms of complexity or whatever. We think that there might be some way.
I don't know Whitehead, but it can't be conceptually simpler.
No, Whitehead actually.
You are using Rosenman.
I'm using Rosenman. Yeah, Rosenman is not. There are some. It's not. It's elementary. Rosenman is elementary. It's not very simple, but it's elementary. We think there might be a hope to actually do it more geometrically, and something that resembles Whitehead. But the point is that, I mean, Whitehead, the cut vertices of Whitehead only encode automorphisms of the free group, and here we need something much. We need many more automorphisms because, of course, every automorphism of the free group is also an automorphism of the free group algebra, but there are many more. So it will not be enough as is. So okay, so yeah, I think I'm done here. Yeah, thank you.
Okay, do we have any further questions? Yes.
Yeah, suppose you're given a two-sided ideal. You want a basis sort of as a two-sided ideal. Or does it exist? Do you know anything about it?
So you want to have a unique representation. Yeah, I'm not sure. I mean, so you want a unique representation when you can multiply from both sides.
This might be.
Yeah, no.
I mean, you might try do a Wedderburn theory, but I think that with a free group, the representation theory is extremely hard to decompose. If you get too far on this, I'd imagine you're running into problems.
Or
Like you look wide in both.
sure, or even not just a basis, even just checking that a generating set is minimal, generates ideal, something like.
Yeah, no, I don't know about it. I think yeah, no, that's a very basic question that are still open, even for I don't think it's
I have a question. So you mentioned this recent result of Huygens Ryan, right? And his paper is about free group, but I believe he mentioned his arguments, I believe, to work much more general. Maybe there are some papers and preparations. And I wanted to ask about your results in more general, for what other groups you can expect. And one of the questions, if you have a fully resolutely free group, is there any chance to expect something similar?
yeah, okay, I didn't think about anything of this sort at all. I mean, oh, okay, you know what? It's a good. I mean, of course, I mean the notion of primitive is not very perhaps you want to think about free extension, when one thing is a free sum out of another. And then, yeah, it's a good question. I mean, you can. Yeah, but, okay, but, I mean, if you don't have the basic result that things are always free, it's not even clear how to define the duality. Yeah, I don't know. I didn't think about it. We didn't think about it, so I'm not sure.
I mean, I think the divisor problem is solved in some group. I mean, usually you have to go to infinity, like you go there and see what you're doing and then come back in. So if you sort of understand the boundary of the group, then sometimes you can answer these kind of questions, even more general ones, like bounds constant things like that, which in the C-star algebra rather than in the just this pure algebra, group algebra.
Yeah.
But these things, the minute you get away from very structured groups.
Yeah. Oh, even for.
Yeah, even for anything non-free as far as you.
Yeah, even surface groups or, yeah, I don't know what's. Yeah, here we strongly use the Nielsen-Schreier, the Conley-Wint result. I'm not sure what you can do without it.
Any further questions, or are we? Well, thank you for organizing, Anna, and everyone, and
Let's thank the organizers and speakers.